Now a car of mass 900 kilos travelling with a velocity of 2.5 meters per second strikes another car of mass 1500 kilos which is stopped at a set of traffic lights. So here's our stopped car, okay, and here's our approaching car, so it's heading this way, and this guy here has a mass, let's call this car 1, right, and this car 2. So the mass of car 1 equals 900 kilograms, and the mass of car 2 equals 1500 kilograms, right, and the velocity of car 1, so V1, velocity of car 1 is 2.5 meters per second, and the velocity of car 2 is 0 because it stopped at the lights. The lights must be red, right? So first question, part 1 there, is to calculate the momentum of each vehicle before the collision. Now, momentum is got by multiplying the mass by the velocity, m times v. Sometimes that's written with a Greek symbol like that, rho equals mv. So the momentum of vehicle 1 before the collision, rho 1, equals m times v, so that's 900 multiplied by 2.5, and that comes out at 2250, and that's going to be kilogram meters per second. Let's move this baby up here a bit. Okay, and the momentum of car 2, rho sub 2, before the collision is going to be the m times v, and the v is 0, so we're going to have 0 momentum, 0 kilogram meters per second. Then part 2, then the total momentum, well, the total momentum, momentum T for total is going to be rho 1 plus rho 2. Adding them two numbers together, we get 2250 kilogram meters per second. So that's the total momentum before the collision. And then we're looking, part 3, the common velocity of both cars. The common velocity of both cars after the collision. So after the collision, what's going to happen? Well, after the collision, this car and this car are going to be welded together, and they're going to be heading this way. So that's car 1, that's car 2. And the momentum, the law, one of the laws there is that the momentum before and the momentum after have to be equal. So we know that the momentum before, the total momentum before, the total momentum after have to be equal. That's the total momentum before the collision. And the total momentum after the collision will also be this figure here. But after the collision, they'll be behaving as one vehicle. So what can we do with that? Let's see now. Switch to black. So after the collision, the total mass, the mass of 1 plus 2 will equal the 900 plus the 1500, and that gives us 2400 kilograms, 2400 kilograms. That's the mass after. The velocity after the collision we don't know, but it'll be moving down the road a bit anyway, in this direction here. It's supposed to be an arrow. So we know, according to the law of conservation of momentum, that the momentum before, the total momentum before equals the total momentum after collision. So the total momentum before the collision was 2250, and that's going to be equal to the mass after the collision, right? That's the mass of 1 plus 2 times the velocity after the collision. Now we know that the mass after the collision, the mass will just be the mass of the two items added together. So that's 2400 multiplied by the velocity of the two items welded or stuck together. I'll just drag this up here a bit. So to work out the velocity after the collision, we'll divide both sides of the equation here by 2400. So that equals 2400 divided by 2400 multiplied by the velocity. They'll cancel, and we're left with this fraction here, 2250 divided by 2400 gives me 15 over 16, or 0.9375, or 0.94 to 2 decimal places. So the velocity after will equal to 0.94 meters per second. So that's the total velocity. That's the velocity after the collision, and they'll be heading that away, according to our drawing. Okay, part 4. Calculate the loss in kinetic energy. Calculate the loss of energy due to this collision. Explain where the energy goes. Right? But before the collision, the kinetic energy, it was a half times mv squared. So the only vehicle that had kinetic energy before the collision was the only one that was moving, the only one that had velocity, was the 900 kilo. So that's 1/2 multiplied by 900 multiplied by 2.5 squared, right? So that's going to be 450 multiplied by 2.5 squared, and I get 2812.5. That's energy, so that's joules. So after the collision, the kinetic energy still equals a half mv squared, but this time the mass is going to be 2400, and we worked out our velocity at 0.94, and we're squaring that. So we'll bang that into the calculator, and we get 1/2 by 2400 gives me 1200 multiplied by 0.94 squared, and I get 1060.32 joules. So that's the kinetic energy before the collision, and that's the kinetic energy after the collision. So there's a loss in kinetic energy. Where does the kinetic energy go? So lastly, we want to explain, where does the kinetic energy go? Why is there a loss in kinetic energy? Well, maybe I'm not particularly sure about this, but there can be deformation, right? So the two cars bang into each other, and there's a lot of energy used up in the changing of the shape of the cars. Heat, the molecules or atoms in both cars can heat up and move around faster when they bang into each other. So yeah, deformation, heat. That's about all I can think of for now. Anyway, if you find out a better answer, please let me know.